Okay, so now we're going to talk about applied hash functions, and particularly hash functions applied in blockchains. So we will first recap what a hash function is, and then we'll start talking a bit about cryptocurrencies and what the main problems are there that we need the hash functions to solve. And then we'll see chaining and blockchains and proof of work, which are two solutions to problems that we need. And finally, we'll see tree hashing, which is also another solution to another problem that we will see. So let's start talking about hash functions. So what are they? So hash functions, or rather cryptographic hash functions, are so-called one-way functions. This means that they have some desirable property that you can go one way easily, but it's very hard to go the other way. So what does this mean exactly? So it's commonly referred to as three different properties. So pre-image resistance is the first one. This means that if we have a hash function edge and a value y, then we should output any x such that h of x is equal to y. That is, we are supposed to find the inverse or the pre-image. So y is the image and x is the pre-image that we are supposed to find. And if a hash function is pre-image resistant, then this is very hard. This also another name for this is one-wayness. So pre-image resistance or a hash function being one way. The second property is second pre-image resistance, or also known as weak collision resistance. So in this problem, we get a hash function edge, we get a value x this time, so the pre-image. And then we should find any x prime such that h of x is equal to h of x prime. And of course, x and x prime should not be equal. It should be two different values. So we should find a collision. Given a pre-image, we should find a second pre-image that also hashes to the same value. The last property is the collision resistance, or strong collision resistance, as it's sometimes called. And in this case, we get a hash function edge, and our job is to find x and x prime, any one of those. We may choose them as we like. The only requirement is that h of x is equal to h of x prime. They shouldn't be equal, of course. So two different x and x prime. And if we can find any one of these, then we say that we find a collision. So if edge is collision resistance, then finding x and x prime is very hard. So that's a secure cryptographic hash function. It has these properties. Now let's proceed to cryptocurrencies. So the idea of Bitcoin, the first cryptocurrency that, well, first modern cryptocurrency that we think of. There were some other cryptocurrencies before, which were digital cash, but they are not the same as cryptocurrencies as in Bitcoin and Ethereum and others. So the idea of Nakamoto's Bitcoin was that it's supposed to be decentralized, so we have no central authority, like a federal bank, for instance, in the normal monetary systems. And all transactions are in a public log. And this makes it sort of democratized, because it relies on majority consensus rather than an authoritative national bank or federal bank or whatever. So this was the idea. And the key is in that all transactions are in a public log. That's the key idea of this. So because this means that a transaction is money. So there is no money because that's what digital cash was, or normal currency that we use. Then you actually have money. But here, you actually don't have any money. You just have transactions, and you have transactions saying that this public key has this much value, and then you can transfer money from one transaction to another, essentially. So if we look at this figure, we have that each of these are transactions. Then for a transaction here, you have the owner of the transaction, which is the recipient of from another transaction. So we see here that this transaction goes into the next transaction. So this one goes to another owner. So it's this owner of a transaction that can actually use it. So the way this works is that this figure is transactions transferring from owner 1 to owner 2 and transfer them to owner 3. So what happens is that you have the owner's public key, which is stored in the transaction, and then the owner has the corresponding private key, and you need that to use a transaction. And what you do is that you compute a hash from the owner's public key and the previous transaction that you are using. And then you actually sign this. This needs to be signed by the previous owner. So when owner 1 here wants to make a transfer to owner 2, what happens is that we have owner 1's public key that can be used to verify owner 1's signature here. So since owner 1 has money according to this transaction, owner 1 can create a signature to create this transaction, put owner 2's public key, so the recipient, put that into the hash and put the actual transaction into the hash, and then you sign it. And suddenly whatever was in this transaction now went over to owner 2, because there is a signature by owner 1, so everyone can verify here that owner 1 here has signed here, which means now it's owner 2 who owns this. So transfer of ownership. And since there is such a signature, there's nothing owner 1 can do to retract this. And then it happens the same when owner 2 wants to transfer to owner 3. That owner 2 here creates a new transaction here, uses the private key to sign. The hash is from owner 3's public key and this transaction, so these are linked. And then it's owner 3 that owns this. So this is the idea, the main idea. We will get more details later of how these cryptocurrencies work, particularly blockchains, or rather decentralized ledger technologies, as they are more appropriately called. And another one of these problems that we have, that we must face in this system, is how to distribute transactions in the network, since, well, there are going to be a lot of people interested in these transactions and what happens, because if they are going to receive payment, they need to know if the one who is actually paying me has actually made a transaction, so I actually have received the money or not. So if we look at this figure, we have Bob here that has a transaction that, yeah, maybe one of those transactions that we just saw. And for everyone to know about these transactions, Bob has to send them to everyone else in the network, as we see here. And that's pretty easy, it's just to send them. However, we focus on security here. So of course, Bob can maliciously distribute transactions. So while he did send this transaction to someone, he creates another transaction where he tries to spend the same money or the same transaction, but on something else. So pay with the same money twice. And of course, that shouldn't work in a functioning monetary system. So in this case, he has a separate transaction that he sends to this person. And then Bob will attempt to get both these transactions into the chain here. That is the idea. And of course, that is not acceptable. So that is one problem. Another problem that we have is, yeah, of course, this can happen, even not maliciously. And then the question is, how should we agree on this chain? Because different people receive, even if everyone receives all the transactions, they might receive them in different order. And then the question is, what should the transactions look like, and in what order should they be, and how can we agree on this? Because everyone in the system must agree on exactly what this log looks like. So in this case, we have the people running just storing the log. Since this is a decentralized system, everyone participates in storing the log. And this is the visualization of the log. So these people have one block that they want to submit, one block each. This guy has managed to make 2 blocks that he wants to get in here. And this guy has none. And then we have these options. So this is what the chain looks like. This is an alternative to this and this and this and this. These two are just alternatives to each other, but we want it to look like this. So how do we agree which block should be at the head? This one, or this one? And then if we agree on this one, we should also replace this one by this one. So how do we do this? That is the other problem that we are facing. So let's go to the solutions. So how we can actually solve some of these problems. So let's get into chaining and blockchains. So as we said, we must order the transactions to prevent double spending, because we don't want to allow anyone to pay with the same money twice. That's not appreciated. So how do we solve this? So the idea is to create a simple time-stamping mechanism. And I put time-stamping in quotes because it doesn't really timestamp, it just creates an ordering. So the idea here is that we take a block with lots of items in them, and we put them into a hash and compute a hash, and we also put in the hash value of the previous one. So when we created such a block, we can create a new one by adding new items and then hashing all these together, putting them in a hash and including the hash of the previous block. This way we create an ordering, because it's obvious that these items must exist after these ones, since these are included in the hash here that is included in this hash with these. So we create a sort of ordering. So this is an ordering of the set of transactions, and it's actually quite similar to the commit objects in Git. So same idea that we have there. Then the question is, what prevents me from forging a block and claim it was before another block in the timeline? So taking, for instance, an item from here, claiming it appeared here. What prevents me from actually doing that? So the solution to that question is that the block that I forge must have the same hash, which means if I want to forge, make changes in one of these blocks, it needs to arrive at exactly the same hash as it had before, which means the edits I make here must not change the hash. This means we must find a collision against this hash function that we have. So, or rather, find the second pre-image, because we have one image, we have the hash value it gets, and now we need to find a second pre-image which gives exactly the same image, but with the desired modifications. And this was a hard problem. If the hash function is a cryptographic hash function, then this is difficult to achieve. Now, let's get into proof of work. And this is very interesting because this will actually sort of violate what we just said. That was hard, but in a clever way. So we'll see. So the question is, why do we need proof of work? And that is because the blockchain is not fixed. It's never fixed. It's continuously extended, and someone can change the history. It's just a matter of making the others agree that this one appeared before. So technically, we can rewrite the entire chain, but we need to convince others that this should happen. Remember, we had this picture, how our blockchain is agreed upon. So we need to convince people that this is actually what it looks like, and we want to prevent people from this one to go back several blocks to do edits and submit them and say that, hey, this is what the blockchain should look like. And convince the others to change their view from this or this into this one. So how do we do this? So the idea is that we want to prevent this forgery, because technically these are just computed hash functions. So if we can just go back and this is what it looks like. We can just go back and redo these computations, but with different values, and arrive at a different head of the chain, and then we can make it the longest chain, longer than the others, because the consensus algorithm in Bitcoin, for instance, that one says that it's the longest chain that is the valid one. So say that if this guy adds one more here, then it should be another one here too. Then this one is obviously the longest, and this means that we should dump these two, which are actually the valid chain, and change to this one. So this is easily doable with just the construction that we saw before, because we just need to recompute these hashes, and we can do that pretty instantly. So how do we fix this problem? How do we make it hard to change the history? Well, we introduce proof of work. So the idea here is that we adapt the blocks that we saw before. So we had the previous hash and we had the items before, but now we add a nonce value here, so a number used once. So we see here that the next block here is based on the previous block plus the transactions and the nonce now. So this n wasn't here before on the slide before. And then we also introduce this requirement. And this is what causes the proof of work, because this actually causes quite some work. So what will happen here is that we require the hash, so the image, to be less than a particular value, which means we cannot have just any hash, can't just compute any hash because that might not be less than k. So what we have to do here is to vary this nonce and try to find a nonce which, with this edge I-1 and this bi, will yield an edge I less than k. Because this k is the difficulty that is adjusted so that one of these problems can be solved like every 10 minutes. So if we set this k very large, then of course this problem is going to be much easier. If we set it very small, then this problem is going to be really, really, really hard. So we have to adjust this k, and in Bitcoin's case, we adjust it so that one of these problems can be solved every 10 minutes. And this is adapted because the size of the network might change and be different. So different amount of nodes participate in the network to solve these problems. So the idea here is that we have the proof of work problem, which is this, and then we have k, which is a value. So an L bit, we assume it's L bits long, so it's less than 2 to the power of L. So that makes it this long. And then if the image, so the hash value y, has to be less than k, that means that this part is actually fixed to zeros. So then we have a fixed pre-image, which means we don't have such a difficult problem after all. It's not like finding a pre-image, but rather somewhat like that, because we are still allowed to vary here. So if we compare this to the pre-image problem, then the entire thing is fixed. So we have to find this exact one. There is only one that we have to find, which is 1 out of 2 to the power of 256 possible ones. But if we look at the problem, the proof of work problem, we see that it's only this that is fixed. So there are these many bits that we can actually vary, that are allowed to vary for this to solve. So it's a much easier pre-image problem than the actual pre-image problem. And by varying k here, we vary the L bits that are here, which means we can control how difficult it is. So if we shrink k, that means it shrinks in this direction. That means the fixed pre-image is increasing. So if we set k to like 1 or 0, then it's all the way down here. So then we have the full scale cryptographic pre-image problem. So we can control how difficult the pre-image problem is supposed to be. Now let's go to tree hashing. Remember that we had this time-stamping mechanism, and this is to prevent forgery, which means that we need to verify whenever there is a new transaction that uses an old transaction. We must go back and find that old transaction in some block and then check that it has not been used in any other block since then. So this is computing a lot of hashes, and we would like this to be efficient. That's why we use a so-called Merkle tree. So the idea here is we want to include these data blocks, so L1, L2, L3, L4, and create a hash for them, and then be able to check if one was present. So the way we do this is that we hash each of them. This creates a hash value. Then we hash these hash values. So we create a tree structure, and then we hash these, so we get the top hash. And we can do this for transactions in this way, because the advantage here now, if we want to verify that this transaction 3 actually is in this block, then we take this, compute the hash of it, then we get hash 3, which we don't need to have because we can compute it. We need hash 2, but we don't need to have the transaction that generated this hash, because that one might be much bigger than the hash value. So this is saving us from space, because the hash value might be 256 bits or say 512 instead of several megabytes that the actual transaction might be. So then we have saved a lot of space by just having the hash value here instead. We can hash this one. So now we have the two hash values. We can compute this one, but we also need the other leg of this tree. So we need this hash instead of all the transactions and hashes that it represents. We can hash these together, we get the root, and we see that everything computes. So this means that we need to store much less data to do the verification than we would have needed otherwise. So this helps us make things a bit more efficient. And that was everything that I wanted to say about applied hash functions and blockchains.